Alright folks, so I'm sure that you guys have been looking forward to this as much as I am. The very last lecture that we'll be doing this course. I'll be doing some examples after this, but still. We'll be talking about combined loading. So again, we've been looking at normal and shear stresses on an element. So we want to be looking at what happens when you superimpose multiple stresses onto an element caused by multiple loads. As well, we'll be looking at how the orientation of our frame of reference affects how we view the stress. So when we have combined loading, it's based upon the principle of superposition. So basically, if you take a load, you can break it up into multiple parts and apply those loads separately, and basically the combination will be the same. So if I have this rod here and I apply a 25 kilonewton force to it and also apply an additional 10 kilonewton force to it, the end result will be the same thing as if I had just applied a 35 kilonewton force to it. So those can be broken up. And again, we are making the assumption here that we are operating in the linear region, so we're not yielding yet at this point. But that's again typically the condition that you're going to be designing for, anyways. So, quick reminder about what type of loads occur. So we got our axial loads. They're causing stress. That stress is oriented perpendicular to the cross section, and again, typically just assumed to be distributed uniformly, which is a reasonable assumption based upon St. Venant's principle, as long as you're reasonably far away from where the point of application of the force is. So again, that's just the force over the cross-sectional area. Got our shear loads, those cause shear stress, and that's distributed according to our VQ over IT. So as our position varies throughout the cross-section, our Q is going to vary. And our T might vary too, depending upon if the cross-section has a constant thickness or not. Our bending moment, its stress is going to be perpendicular to the cross-section, and it's again distributed according to the negative moment times y over I. Again, that y is measured from the neutral axis of the cross-section. And then we got our torsion. It's causing shear stress as well. So it is going to be equal to the torque times the distance from the centroid. I don't know why the textbook used rho for that. It's rather annoying. But anyways, distance from the centroid divided by our j. So again, linearly from the center. So as an example, if we have some sort of normal force and we have some sort of bending force, and we apply those both at the same time, it's going to cause a change in the distribution. So in this example, we'd end up we're pulling on this thing, so it's going to cause a uniform tensile force, and we also have a positive bending moment, which means that it's causing compression at the top, tensile at the bottom. So what happens here is at the bottom, the tensile, this tensile force and the bending moment cause a larger tensile force, whereas at the top here, the compression and the tensile cancel out somewhat, so it's less there. It also shifts the point of zero stress up from the neutral axis of the bending moment to another point. based upon kind of the ratio of the normal forces and the bending forces. So yeah, typically speaking, you tend to have bending stresses imposed at the same time as some sort of shear stress, because again, adding a shear stress is what causes bending moments as you move along. So basically, your bending moment is equal to the integral of the shear stress diagram. So that it's the shear load that causes the bending stresses to arise, the bending moments to arise. So those cause the bending stresses, and then the bending stress is a direct function of the moment, and the shear stress is a direct result of the shear load. I guess we're a bit off center here. There we go. That's better. And then, of course, the magnitude is going to depend upon the vertical position in the structure. So, again, the point at which the maximum bending stresses occur is always going to be the point that's the furthest from the neutral axis. Whereas the point where the highest shear stress occurs is the point where your Q term is the highest, which happens at the neutral axis, because your Q term is basically, so your Q term is based upon, here's our neutral axis. If we're looking at the stress along a certain point, along say this point, we're basing the Q term off this area times its y bar. So if we're at the neutral axis, then that's based upon the entire area times its y bar. So the area grows the fastest. And then, of course, if we're below the neutral axis, so if this is the neutral axis and this is the line we're looking at, we shift to the area below the neutral axis. The area kind of separated from the neutral axis by that point. So you tend to get, at least with members of a constant cross section, it's a quadratic formula that gives you the stress variation as a function of the vertical position. So let's have a quick look at this one. So if we have this set up here, we want to figure out what our maximum allowable, what the normal stress would be. Caused by the, so we're looking at the normal stress here. We're not, so they didn't ask for what the shear stress would be, but if we have this thing here, actually here I'm gonna shrink that down a bit more. Okay, so if we got this structure here, we're going to want to, again, start with the free body diagram. Let's call this A, let's call this B. Going to have an AY, going to have a BY. We're also going to have an AX, but in this situation, there's no other X, so AX ends up being 0. Then we got this 300 kilonewton force here. 1 meter between there and there, 2 meters between here and here. So we want to figure out what our by is and or ay. We can just go ahead and solve for take the sum of the moments. Let's take the sum of the moments at A. It's equal to 0. So 0 is equal to negative 300 kilonewtons times 1 meter minus 3 meters times by. I'll say plus. That's a plus because it's clockwise from there. So by ends up being equal to, well, that'll be 100 kilonewtons. Which means that when we take the sum of the forces in the y direction, 0 is equal to ay plus by plus 100 kilonewtons minus 300 kilonewtons, which means that our ay needs to be 200 kilonewtons. So if we draw a shear stress diagram, I'm going to start with ay pushing this up to 200 kilonewtons. And we hit our load there. That drops us down. That drops us down 300 kilonewtons to minus 100 kilonewtons, and that stays constant until we hit our support here at ay, which brings us back up to 0. So again, a positive, negative. So if we were to integrate our our shear diagram in order to find our moment diagram, well, we'd start off at 0 because it's a pin connection, and then we would increase at 200 kilonewtons per increase at a rate of 200 kilonewtons. So if we go over that 1 meter, that would bring us up to 200 kilonewton meters. And then over this span here, it would drop down at a rate of negative 100 kilonewtons. So over a span of negative 100 kilonewtons times a 2 meter span drops us down 200 kilonewtons, which brings us back down to 0. So that means the point where we have our maximum stress, a maximum bending moment is there. It's 200 kilonewton meters. So if we want to calculate our bending stress, we need to basically figure out how this thing relates in terms of basically where the neutral axis is on this structure. So actually, I'm gonna I want to do this. There we go. So basically, we need to find the centroid of this spot here. So basically, measuring from the base here are... Oh, actually, never mind. They told us where the y-bar is. Well, you could have calculated it. So they told us what the y-bar is. We were given the Ix. So we know that the bending stress is going to be equal to negative the moment times our y position divided by I. So basically, if we want to solve for that in terms of our y position at that point, that's going to be equal to negative 200 kilonewtons meters times y divided by 2.50 times 10 to the 8 millimeters to the fourth. So, based upon that, I'm probably going to want to kind of put things into, well, here, let's pull out our calculator. So negative 200 divided by 2.5 E8 that gives us negative 8 times 10 to the negative 6. And what's our units here? Kilonewton meters per millimeter to the fourth times y. So I'm going to want to put everything there in terms of millimeters, because our y measurement is going to be in millimeters too. So if we put everything there in terms of millimeters, then we multiply our m, well, multiply this value by kilonewton meters times 1,000 millimeters per meter. Cancels that out. And let's put it in terms of newtons as well. So we can throw a 1,000 newtons per kilonewton in there. So we can multiply that number we had by 1,000 and then multiply it by 1,000 again. And then we're given our bending stress as negative 0.8 newtons. And what we got here? We got millimeters on the top, millimeters to the fourth at the bottom. So we cancel out one of those. That gives us millimeters to the third. Newtons per millimeter third times y. So when we plug in a value for y that is in millimeters, one of these is going to cancel out, and we're going to be left with newtons per millimeter squared, which is a megapascal. So what we could also do here is negative 0.8 megapascals per millimeters times y. So our variation there is going to be so at let's see, at a distance of at the top here, the total distance from here to here is 300 300 millimeters from the bottom to the top, which means that in terms of the distance from the neutral axis, at the top, y is equal to 100 millimeters, whereas at the bottom, bottom, y is going to be equal to negative 200 millimeters. So if we wanted to plot plus y minus y, if we wanted to plot our stress, essentially we'll be starting out at 0.4 MPa per millimeter, 0.8, negative 0.8 MPa per millimeter times 100 millimeters, which gives us negative 80 MPa at the top. And then obviously that drops down until it hits the neutral axis and continues going straight. And then down here it should be, again, negative 0.8 times negative 200 millimeters. That gives us 160. So that's just here's the axis for. In green we've got our axis for the y position, and in red we have the axis for our stress. Another way that people sometimes draw this would be something like this, where they indicate with arrows whether or not it's a compressive stress on the top or a tensile stress on the bottom. So basically, whether or not, if you cut the face out, whether or not we're pressing into that face at the section cut, or whether or not we're pulling away from that. I tend to prefer this one because I think it's a bit less, this one here, because I think it's a bit less obvious, it's a bit more obvious as what's going on, but either way works. So in that situation, we did not exceed our maximum allowable stress of 350 MPa. Yay! So what if we have this set up instead? So we got it pinned at one end. We've got the same load. Got the same loading situation going on. Supports are in the same places. So the shear stress that's going to be occurring is going to be the same. The shear load that's going to be arising is going to be the same. The bending moment that's arising is going to be the same, but we're going to have axial stress in there as well. So basically what's going to happen is we're going to end up solving, and we're going to get this same situation for the bending stress, but we also need to deal with the axial stress. The axial stress, or the normal stress, or whichever of those you want to call it. So it's relatively simple here. What we need to do is we need to go ahead and calculate what that axial stress would be. So again, the axial stress is going to be assumed to be uniformly shaped, uniformly distributed over the cross section, especially over this cross section here, because it's it's 3 meters away from where the loads are applied on this end. It's a meter away from where the support is on the other end. That's far enough away that all this stress will have a chance to be evenly distributed. So the magnitude of that stress, let's call it, the normal stress, that's just going to be equal to 5,000 kilonewtons divided by that area. 3 times 10 to the 3 millimeters squared. So I'm just going to put that in terms of newtons per millimeter squared. So 500, so 5,000, no, 5 million newtons. Once we take out that kilonewton, and then 3 times 10 to the 3 millimeters squared. So 5 million divided by 30,000. That gives us 166.6 megapascals. Newtons per millimeter squared is a megapascal. So what we do with that is we take that and we add it to what we found here. So basically, here, let's do a little copy and pasting here. So we have this, and we also have a solid 166. That's a tensile force, tensile stress. So we need to take those two lines and add them together. So basically, we're shifting this part of the diagram 160 megapascals to the left, which would end up to be right about there, actually. So here, minus 180 plus 166. Sorry, minus 80 plus 166. That'll give us 86.6 megapascals. And then over here, we get the 160 plus the 166. So that'll be 326.6 megapascals. So let's delete the old lines. I'm trying to delete you stupid. There we go. So that's our new stress distribution. So again, it's we don't have any compressive stresses, but we still have a bending moment because the tensile stresses that we do have aren't uniformly distributed. You don't need compressive stresses to cause an overall bending moment. You just need uneven distribution in the tensile stresses that you have in order to result in the same bending moment. So this is what we ended up with for our result there. So again, just going back here. Okay, so it's not quite within the failure limit for what they asked for. Close to it. Oh well. So yeah, then we are able to basically go ahead and yeah. So that's an example. So what we tend to do is we want to basically figure out what sort of your loads you have. So at a particular point, what's your axial load, what's your shear load, what's your torsion load, what's the bending load at that point. Then use the methods you figure that out using the various methods that we talked about. You know, if it's a determinate structure, then it's simple. If it's indeterminate, it's not so much, but oh well. Then you figure out what sort of stress components are associated with each internal load component. You might be doing that for the entire section or perhaps for an individual point of interest that you were asked for. And then you just add stuff together. Just always keep in mind your orientation and what face the stresses are acting upon. So then you superimpose the normal stresses and superimpose the shear stresses, either adding or subtracting them together if they're opposite signs, and then that's the result for what you're looking for. So let's go for another quick example. We have this force here, this block. We're applying a force kind of at the edge, and we want to figure out what the stresses would be at these points C and B here. So having a look at that, if we wanted to be essentially in equilibrium here, kind of if we're examining the situation that's going on kind of here, what's going to happen is in order for this, this cross section to be in equilibrium, what's going to have happen is you're going to have basically an equivalent axial load and that axial load's going to be equal to 15 kilonewtons. And you're also going to have some sort of bending moment, because again, it's not applied at the centroid, it's applied 50 millimeters off from the centroid. So the bending moment that you, yeah. So your bending moment is going to be equal to the 15 kilonewtons times the 50 millimeters. 50 kilonewtons times 50 millimeters gives us 750 kilonewton meters. Sorry, kilonewton millimeters. So we're far enough away from the point of application of the force that we can expect that the axial force here is going to end up evenly distributed. So that'll be a negative, because again, it's a compressive force. So, oh yeah, compressive load. It's a compressive load, so it's a compressive force. So that'll be negative 15 kilonewtons divided by our area. So our area is 40 millimeters times 100 millimeters. So let's see, 15,000 divided by 40 times 100. That gives us negative 3.75 MPa. And then you're going to have the stress distribution due to the bending moment portion. So again, our stress there is equal to negative m times our y all over I. So our I, when we go to calculate our I, you just got to keep in mind kind of the orientation. So again, we're kind of off, because of the manner in which this thing is offset, the rotation it's going to be inducing is going to be about this axis. So let's call that the z-axis. Z-axis. Let's call this the x-axis in this direction. Let's call this the y-axis. So our IZ here, again, IZ is going to be, IZ's always 1 over 12 base times height cubed. But that's when we are rotating about an axis like this. So here, the h value that we would use will be 100 millimeters. The b value that we would use would be 40 millimeters, because we're kind of again we got to reorient ourselves such that this is the axis, since this is the axis that we're trying to rotate about in this the z-axis there. So okay, so 40 millimeters times 100 millimeters cubed over 12. 40 times 100 to the third divided by 12. That gives us an I value of 3.3, repeating, times 10 to the 6 millimeters to the fourth. Okay, so we've got that. We also know that essentially when we apply this, I'll kind of let me just copy and paste this. I'm going to rotate it, assuming OneNote lets me do that. OneNote doesn't let me do that. Damn you, OneNote. Okay, I'm just going to redraw it. So if we apply a force like this, what's going to happen here is it's going to kind of cause this bar here to kind of bend like this. It's going to bend like this. So again, we define positive moments as ones that cause these smiley face type bending moments. So this is going to be a positive bending moment. So kind of when we're measuring y in this direction, it'll be a positive bending moment, and when y is increasing, we get more compressive at the top, which isn't surprising at all because, again, we're applying a big compressive force immediately above that. So our sigma bending as a function of y, that's just equal to, again, negative m times y over I. So we have the 750 kilonewton millimeters. So, okay, got negative 750. I'm going to put it in newtons and millimeters. So 750 kilonewtons is 750,000 Newton millimeters times y all over I. So 3.3 repeating times 10 to the 6 millimeters to the fourth. So 750,000 divided by 3.3 E6. So that'll be negative 0.225. And then let's see, the millimeters here cancels out with one of these. So again, newtons per millimeter third y, or as we saw before, megapascals per millimeter times y. So we kind of plot how that distribution is going to occur over the face here. So we got our compressive stress. So the compressive stress is present from the axial, again uniformly distributed, negative 3.75 megapascals. And then we're going to get this bending stress here. So the bending stress is going to vary based upon the distance from the neutral axis, based upon this formula that we got right here. So again, the y value that we plug in there, again our y coordinates, this axis right here, I'm going to put it in red, right here. So it varies from at the top here, or corresponding to the C of 50 millimeters, and corresponding to the B of negative 50 millimeters. So negative 0.225 megapascals per millimeter times 50 millimeters. That gives us here that's going to be so that's negative 11.25 megapascals. That's compressive. And then tensile over here, 11.25 megapascals. And again, that's kind of distributed over the entire face. So here, uniformly distributed, whereas here, it varies based upon that distribution here. So basically what we need to do is we need to take this distribution on the left, on the right here, and add it to this uniform distribution here. So we end up getting this. A positive 2.5, negative 2.5 megapascal compressive force, and a plus the, at point B, it's a positive 11.25 megapascal tensile force. So those two values cancel out to give us 7.5. Whereas at C, we got an 11.25 megapascal compressive and a 3.75 megapascal compressive, which add together to give us 15 megapascals. So that's our combined loading for that situation. So next up, we'll be talking thin-walled pressure vessels. So these are things that hold liquids or gases at high pressure. Typically speaking, much higher than atmospheric pressure. So, a few examples. We got, propane tanks, scuba tanks, so on and so forth. So, generally speaking, the spherical form is optimal, but it's harder to manufacture. The cylinders do suffice, except for some extreme cases, and they're a lot easier to make, so we tend to see that more often. If we are going to be considering it a thin-walled pressure vessel, then the internal radius needs to be at least 10 times more than 10 times the thickness of the wall. And if that's the case, then we can generally assume that the stress state's going to be uniform through the thickness of the wall. So it's thin enough that there's not really any real variation going on there. So if we have something like that, so if we have a spherical pressure vessel, and we take a slice through it, then basically we know that the force needs to be equal. The forces need to balance out. So we got the pressure here, got the internal pressure, and that internal pressure is acting on an area that is equal to the area kind of at the internal cross section. So pi times r squared. R squared is the internal diameter there. And that pressure needs to be equal to the and those forces need to balance out with the stresses induced. So the stresses induced is just going to be that stress there. The force caused by that stress induced is going to be that stress there times 2 pi r, aka the circumference of this circle here, the circumference of the circle here, times its thickness. So basically the surface area of the cut you're taking. So you can just solve for the stress that gets induced. That's just going to be P times R. So for spherical pressure vessels, we get two types of stress that arise. So the first one we're going to talk about is the hoop stress. So again, it's the stress that's kind of oriented around the circumference of the pressure vessel. So again, the force exerted by that needs to be equal to the force exerted by the pressure. So again, the force exerted by the pressure is just going to be the pressure times, again, this rectangular cross section here. So basically, that's how much it's going to be pushing this way. So that rectangular cross section there is just going to be twice the radius times dy. So again, we're taking a small slice the thickness of that slice is dy. And the force that's going to be the stress that's induced, that's going to kind of be holding it in place. That's just going to be, again, the thickness of the skin times that dy is going to be the cross-sectional area of each of these, and the stress is going to be evenly distributed across that. So that stress times this times that area times 2, because we got one on each, one on the top and one on the bottom. So solve for the stress. It ends up being PR over T. So again, P is the internal pressure, R is the internal radius, T is the thickness. And then we also got the longitudinal stress. So again, this is a stress that's oriented parallel to the length of the cross section. So it's you know, whatever stress is resisting you pulling apart the pressure vessel lengthwise, rather than kind of, I don't know, out of in trend. What's the opposite of longitudinal? Transverse. So again, force exerted by that needs to be equal to the force exerted by the pressure. So again, it's pretty much the exact same calculation as you saw for the spherical stress. So you end up getting the same result, because again, the area is the same, the pressure is the same, and yeah, both areas are the same and the pressure is the same. So that reduces down to PR over 2T. So again, your hoop stress is for a cylindrical pressure vessel is always twice the amount of the longitudinal stress. Again, that is why spherical pressure vessels tend to be they're better at resisting the pressure than your cylindrical ones, because they don't have hoop stress in them. We do have radial stresses that technically exist. So again, the radial stresses are basically the pressure that exists kind of in the direction from the inside moving outwards. So if we look at, you know, if we look at a little bit of the skin here, obviously we got pressure pushing on here. So if we look right here, obviously we need to have pressure pushing back. So it technically varies linearly. It's 0 at this end and it's P at this end, and then it drops down as you go through. That having been said, if your R to T ratio is high enough, you have a tendency to completely neglect these radial stresses just because they're small enough that we don't need to worry about them. So as long as your R to T ratio is at least 10 to 1, then the smallest other stress that you would see is going to be, well, your hoop stress is always going to be at least 10 times that, and your longitudinal stress is always going to be 5 times that. So we have tendency to not worry too much about the radial stresses. So we can ignore those and any of the shear stress that would be induced as a result as well. So that's pressure vessels. Stress transformations is kind of the last topic we'll be touching on, and basically the thing you need to keep in mind with stress transformations is that the orientation of the coordinate system you chose at the beginning was completely arbitrary. But the state of stress at a particular point is not arbitrary. It is based upon what loads you apply to this thing. So if you want to be describing the state of stress that arises as a result of whatever loads you put on this thing, you need to figure out how to convert those to a different coordinate system if someone wants to look at a different coordinate system. If you're talking to someone who's looking at things from a different angle, then you need to be able to kind of convert those. So those change of orientations will result in stress states that are described differently, but they are equivalent. So for example, if we have just a bar that we're pulling on, and that's going to cause a certain amount of if we just describe what's going on based upon this coordinate system, we're going to say that, all right, we got this thing here. It's going to cause a stress that's equal to P over A. But if we have a look at a cross section, at a cross section that is oriented with a slant here, the total force across that cross section is still going to be the same. But we're going to have to create it on the basis of some combination of shear stress and normal stress. So the fact that we are looking at things at a slant means that taking a section, if we're examining a cube that's also at a slant, then the stresses that would arise in order to keep that cube in equilibrium need to be shear stresses and normal stresses. So we took something that we initially thought, all right, there's only normal forces there, and we cock our heads a little bit and look at it from a different angle, and suddenly there's not just normal stresses and shear stresses there. Suddenly there's we cock our head a bit, suddenly there's some shear stresses there when there weren't any shear stresses before. So that that's kind of weird, right? So we need to basically be able to kind of describe how those transformations happen. So if we take a cube and we slant it to a new coordinate system. So we started out with X and Y, and now we're looking at a new coordinate system. We're going to call that X prime and Y prime, and X prime and Y prime are located at an angle theta away from the coordinate system we were looking at initially. If we do that, and we have, and we basically take that cube and we kind of examine this face here, which we might have originally, this originally started out as the positive X face before we rotated. But if we look at this face here and a triangle that's composed of sides that are parallel to those two systems we look at, we're going to have a small element here. So that small element, the area of this face is the same. The area of these two faces here are going to be different based upon what angle we move to. And as a result, we're going to get different forces arising. So we are going to get on kind of the force on the faces based upon the original orientation. Again, we're going to just get that area times its reduction based upon the fact that this thing is a bit smaller than the original cube, and the original stress in the x direction on this face, and then of course same idea for the shear. And then on this face we're going to get the same idea, just swapping out sines for cosines and y's for x's. We're going to get a certain amount of force in the x and in the y. And then on the new x prime positive face, we're going to get our new shear x prime times its area, and our new normal x prime times its area, and we're going to get our new shear x prime times its area. And again, the normal x prime is acting in the orientation of the x prime axis. The shear force is acting in the orientation of the new y prime axis. So we can kind of add all those things up in order to figure out how they combine together. So basically what you just need to do is you need to figure out kind of how each of those relate to the new coordinate system. So if we were adding up all the terms in the direction of the x prime coordinate system, so all the forces that are acting in this direction, you're going to get this force here, and you're going to get this force here times cos theta, because again, we got this force here, well, minus that obviously because it's acting in the opposite direction, because again because of our theta's here, we're worried about this component here, so we just multiply that by cos of theta to find out what this component would be. And then similarly, this force here times sine theta, because again, it started out in this direction, and we want to figure out, here, let's start it out down here, and we want to figure out what portion of it is parallel to this axis. So again, that'll be done by multiplying this by our sine theta. And then you just do the same things for this one and for this one, just multiplying by whichever trigonomic identity you need to in order to convert it to whatever portion is parallel to this axis. So again, all that needs to be equal to 0. Then we can just solve for sigma x prime as this, once we throw in a few trigonometric identities as well. If anyone really wants to go through the entire derivation, fill your boots. I personally don't enjoy fussing about with trig when I don't have to. So similar idea for the force in the y prime direction. That allows us to solve for this here, based upon these inputs, based upon the portion of this that's parallel to this axis, the portion of this that's parallel to this axis, the portion of this that's parallel to this axis, and the portion of this that's parallel to this axis. So we're able to solve for that. So yes. So combining other stuff together, more trig identities, we can reduce it down to these two formulas. And then if you want to find out what your sigma y prime is, basically all you need to do is plug theta plus 90 degrees into this formula, and it gives you your sigma y prime. So that ends up being this. And that's how you do transformations. So the interesting thing that occurs when you have plane stress states is that you can always get to a point where you have no shear stress. So there is always an angle that you can rotate to where this is 0. So that basically allows you to calculate what we call the prime stresses, the primary stresses. So there's a particular angle you can rotate to where all you're seeing are stresses that are that are either compressive or tensile normal stresses. This works in 3D as well. I'm not going to go into that for 3D because, again, the math gets really annoying, but it works for 3D as well. So you can calculate your primary stresses by figuring out what you need to rotate to in order to get to this to be equal to 0. And you can also rotate to a point where this is a maximum. And when you rotate to a point where the shear stress is a maximum, you end up getting to a state where the normal forces on all four faces are exactly the same. So they're always, when this is a maximum, the normal forces are always the same. So always a certain amount that is positive or negative. So yeah, that's fun too. And we'll go into some examples.